Recording in progress. This is homework for part C. It's going to be very similar to part B, except now we're looking at a reaction. We have ethanol reacting on a catalyst surface um, to produce acetaldehyde and hydrogen, right? So we will draw this here. This is our catalyst surface. We have our ethanol, and then our two products, right? 1, 2, 3. So we were given a couple of things in this, right? We know the pressure is going to be 101.3 kPa. Our temperature is going to be 548 Kelvin. And then we're given a rate of reaction, right? Our Kr, and that's going to be 10 mole per meter second mole fraction. And we're going to proceed pretty much the same way as we did with homework 3, where we're going to use the Maxwell's equation to try and get a guess by using like our scaling factor and all of that. So we can write our Maxwell equation here. d1 equals dy over dz equals the sum yi and j, right, our mole fraction of component 1 times our flux of 2 minus our mole fraction of 2 times our flux of 1 over our concentration times our dij, right? And we're given our different diffusion coefficients. We have d12 is equal to 72 millimeters squared per second, which is going to be 72 times 10 to the negative 6 meters squared per second. Our D13 is 230 millimeters squared per second, which is 230 times 10 to the 6 meters squared second. And then our D23 is the same as D13 because they're both products, right? So 230 millimeters squared per second, 230 times 10 to the 6 meters squared, right? And so like we did in the last part, homework 4, part B, we can break these down into the individual components, right? So if we're looking at acetone, or ethanol, sorry, acetone, whatever, right? We have our dy1 over dz equals y1 and 2 minus y2 and 1, cd12 plus y2 and 3 minus y3 and 2, nope, y1 and n1, sorry, over cd13, right? And then what we did last time, we used our scaling factor, right? So we said that n, which is a scaling factor between 0 and 1, equals our z over our distance. And we are given a distance here of, we're given a distance here that is 1 millimeter, which will be 1 times 10 to the negative 7 meters. And we're also given our bulk concentrations, right? So here we have our bulk, like before, y1 equals 0.6, y2 is 0.2, and so is y3. So from here, right, we have this, we take the derivative, we get d times our scaling factor, dz over delta, which gets dz equal to delta dn, which we then can turn into a more usable form of dy1 over dn equals dy1 over dz multiplied by dz over dn, right? dz over dn, that's just our delta, or our factor here. So if we plug these in, right, we get dy1 over dn equals, and then it's our value here, and then just the same equation, right? So we can just take that, right, and that is our equation, very similar to what we did in the last homework that I did. We can do the same thing for acetic aldehyde, right? And it will be dy2 over dn, and then it is y2 n1 minus y1 n2 cd12 plus y2 n3 minus y3 n2 over cd23, right? And if you remember last time, we wanted to make an initial guess, right? And so what did we look at? We looked at these things here because we know that this is about 1, and so are all of these here. They will be about 1 because they have to, or because we've applied the scaling factor. So if we look at that, we get that n1 equals cd12 over our delta, which knowing that concentration equals pressure over RT, right? We can plug that in and get PD12 over RT delta, right? And those are all values that are known to us, right? Because the constant, the temperature, the pressure, the D are all given, and so is the delta, right? Um, and so from here, we have to make sure we acknowledge the fact that it's a reaction, right? So we have to include our rate of reaction. So it's going to be Y1 times our flux, right? That equals our rate of reaction, right? So when we do this, we can get a value for our Y1, which will equal KR over N1. And then we can go to our Y2, be 0.5, and Y3, which will be 1 minus Y1 minus Y2, right? So that's kind of how we set up how we're going to be able to make our guesses and what this problem kind of looks like. From here, I'm going to move on and plug this into Excel. And we will go from there. So yeah. Okay, so this is number 4 part C, the Excel portion of the video. I have my notes of what we just did in the first part of this pulled up on my iPad here so that I can put in the equations. These are kind of the preset things, right? These are our initial conditions. At the end of the last part, well, first we said that concentration, right, that equals our pressure divided by our temperature times our R, right? So now we have that value in. And then along with that, we had our values for our N, right? And so our N value here, right, we said that was our pressure times our D12 divided by our R times our T times our delta, right? Because that was CD12 over delta, and we changed the C to P over RT. So we get that value, and then this is actually going to be the negative of this, and there's going to be parentheses around this. Um, and then N2 and N3, right? That is going to be the negative of N1, right? And so, right, then we have um, our values or our mole fractions at the surface, right? Um, and we said that that was just our N divided by our reaction rate, right? And then we said Y2, right? That was 0.5. And we said that Y3 was 1 minus um, Y2 minus Y1, right? And so we get these values here. So now we can kind of set up the the problem here, right? So, um, right, we're gonna have our different steps, right? So this will be our DZ, right? And we'll bring down our steps here. Um, right, series columns to 1,000, and then this DZ value will equal our D divided by 1,000 multiplied by our step here, and that will go all the way down. Um, and I don't want. That's actually incorrect. Oh, this should stay 18. Um, so we can just add the money sign, and then that will populate down. We don't want this in scientific notation. And so we get our values here, right? Then we have our next value. We have our Y1, our Y2, our Y3. And then we have our dy1 dz and our dy2 dz, right? This just is our value at the surface. This is our another value, and then this will equal 1 minus these two things. And then we can do our equation for our dy1 over dz, right? And that is what we worked on in this first part, right? So it will equal our G times our N2 minus our H3 uh, H3 times N1 divided by um, our concentration times our D12, and then plus our Y1 times our N3 minus our Y3 times our N1. And then that will be divided by our concentration times our D13. And we get this value. And this looks correct. What we're going to do here is we're going to take this out of scientific notation. And then this next one, right, we have our second formula, where we get basically the same thing, just using Y2 instead of Y3. So Y2 times our N1 minus our Y1 times our N2 divided by our concentration times our D12 plus Y2 times N3 times N3 minus our Y3 times our N2 divided by our concentration times our D23. And we would get negative 390, right? And then we can use our Euler's method, right, to get these next y values, right? We have our original plus the change times our position, our new position. We can do that for each of these three, right? Our change times our new position. And then this can just come down, this can come down, and this can come down. And escape. That's actually incorrect. Did that change? I don't know why that's doing that. So what we're going to do is we're going to retype this, right? Our B22. Uh, okay, that should work now. And it does. And then we can send all of these down, right? And so when we do that, we get the wrong values up here. So where does that go wrong? right? So what we're looking for, right? So our Y1 bulk, right? Um, we know that down here, this is our bulk, right? So what we expect is these three values to equal zero point 0.6, zero point 0.2, and zero point 0.2. And clearly I have something typed in wrong, but I will go and look and figure that out. But our overall goal will be to get Y2 and Y3, Y1, Y2, Y3 to be the um, corresponding um, value. Right. So I'm gonna pause real quick and figure out what's wrong here. So what I had wrong was my values down here. Right. So I fixed that. So right, I was saying how we want these to get to our bulk values, right? We want them to equal these values here, right? So this is supposed to be zero point 0.6, this is supposed to be zero point 0.2, and this is supposed to be zero point 0.2, right? So we can um, actually find the difference between these two and square it. Um, and we can do the same for this. And then we can get our sum squared value by taking the sum of these two, right? And what do we want? We want that to equal 0, right? And so how we're going to do that is we're going to go into solver and minimize this, right? By changing these two values, right? Our surface, because those are our guesses, right? So if we hit solve here and let it run, it will then solve it for us. Um, and we get um, 4.88 times 10 to the negative 1 and 2.85 times 10 to the negative 1, but our bulk values are exactly what we want them to be, zero point 0.2 and zero point 0.6, right? And this is essentially 0, which is the overall goal of this, right? And so the next part, when we look at this, um, we want if you change one of the other things you can do when looking at this problem is change the size of the catalytic surface, right? And so if we do that, right, we would change our N1 here to our surface value because we know that to be accurate. Um, and then we can look at this. There are two things we can change when we're looking at the um, catalytic surface, right? We can change either the reaction rate or the size. So when we change our N1 values, right, these become different and it starts going to 1 and negative 1, right? So um, one thing that can change here, right? Let's say we change our reaction rate. Let's make this 5. Okay, not 1. 0.00, right? And so we start getting closer to this zero point 0.3 or to this 0.6 and 0.2, right? So we can keep making this smaller and it'll slowly get to 0.6 and zero point 0.2. Right, but you see how as we get smaller and smaller, it's harder and harder to get to that 0.6 and zero point 0.2 value. So the other thing that we can do is we can change this distance, right? So we can make this 0.0001, right? And that will further change our bulk values, trying to get us closer to that zero point 0.6. And that's because you're changing the amount of space that
the reaction can occur on for changing the size. And then for changing the reaction rate, it takes longer and longer and longer to get to your or to for your reaction to occur. And so when you change that, it then changes what will be produced or go into it.